And our speaker is Alexandre Besson from
Good morning.
the Laser 2000 company. So, Alexandre, the stage is yours.
Okay, thank you. This is to move forward.
Yes.
So, good morning. My name is Alexandre Besson. I'm working for Laser 2000 in France. We are based in Pessac, close to Bordeaux, and we belong to Laser 2000 GmbH, based in Munich. So we are experts in photonics. We deal with lasers, with light source, with different kind of camera, hyperspectral camera, multispectral, UV. Is there a way to stop it?
Some automation.
Okay.
You have to take care about and click backwards also.
Okay. It's very stressful. There is automation in the slide. Sorry for that. So we just to talk about the project we made for a startup based in Toulouse. They're requesting a multispectral or hyperspectral system to measure air pollution. And main specification is that this system should work 24/7 automatically without any intervention. Outdoor, it will be placed on top of buildings and acquires a calibrated image at different wavelengths. So, what is next? What's better? Yeah, but green is play. Okay. So first, we worked with this company and we proposed to them some consulting development to check what are the available components on the market to build such system for them. So there were two scenarios. First one, to use a hyperspectral camera, and second one, to use a multispectral or a camera or multispectral system. Just to explain what does it mean, what is behind hyperspectral and multispectral. So we all know a monochrome sensor. It's a matrix of pixels catching images and giving grayscale image. The next step in the industry was color cameras. So we all know about color cameras. Basically, a color camera is a simple multispectral system with 3 layers, red, green, and blue. If you go further in the number of spectrum you can catch with this camera, we go to multispectral camera. And then if you go again further with contiguous bandwidths and a large number of spectrum bands you can see, we go to hyperspectral camera. To go into detail for what different kind of hyperspectral camera, the easiest one to understand is what is called a push broom camera. A push broom camera is based on some sort of optical design, like a prism, and the light goes through the prism and diffracted the light and divide the spectrum on the sensor. So you have different layers in a continuous way, and basically this kind of camera should be seen as a large number of line scan camera close together. So to use a push broom camera, you need to scan. So either what you are scanning is moving under the camera, or you make the scan by moving the camera itself. In Laser 2000, we are working with a great company called Resonon. They have a wide range of hyperspectral camera, push broom hyperspectral camera. So you can see here they have available model from UV to infrared. Now, if we talk about multispectral camera, so it's between color and hyperspectral. Multispectral is number of spectrum, and basically 10 spectrum, 10 or 20 or 30 spectrum, and they are not necessarily contiguous. So there is discrete bands of image. A simple solution is called framing. So framing can be done in 2 ways, using a filter wheel moving in front of the camera, and we are catching with different bandpass filter, different spectrum, or by using light. For example, a not very well-known way of making color images with a monochrome sensor is to use RGB light. You light in red, take an image, light in green, take an image, light in blue, take an image. You put the image together, and you have RGB image. we can do the same with different colors. Just by lighting at different bandwidths, you can build, in this way, a multispectral camera based on a monochrome camera. Another way to build a multispectral camera is to put filters in front of each pixel, and so bandpass filters at different spectrum, and then you have a mosaic of different spectrum image. Still, a well-known example is most of the camera we found today in the industry in color are based on what is called biofilter. It's small filters on each pixel, and it's red, green, and the line below is blue, green, blue, green, blue, green. And with algorithm, you reconstruct RGB image on the whole sensor. Another technology is to put micro lenses in front of the sensor. So it's a way to build a multispectral image, but it's downsizing a lot the resolution. So about requirements for this project, customer would like to use between 6 and 12 bands, a few systems to make in 3-4 years. So it was impossible for us to design, let's say, a multispectral system with small filters based on put on the sensor. It's too expensive for the number of systems we had to make. There is no way to, of course, illuminate the sky, because the application is to measure air pollution in the environment. So the system is scanning open air sky. So it's not possible to do framing by using different lights. And of course, as usual, total cost of the solution is a key factor. So we agreed with the customer to go on a multispectral system based on a filter wheel. How we work with the customer during the first step. We have a short meeting every week to discuss how we advance the component we select. And we also use 3D printers to quickly print small parts to put parts together, for example, like the camera and the filter wheel. To attach them together, we use a 3D printer. And then we start put some bricks together. We wrote the software in-house in Pessac, and we put little by little all the bricks together. And it took 6 months between the end of the consulting part and the delivery of the prototype. So here is some picture of what we did at the beginning. So you see at the very beginning we just have the camera and the filter wheel, so we put them together, and with the laptop we start scanning images at different spectrum to see what we get from the camera. And in parallel, we advance in the 3D design. So you can see inside, you can see the camera, the wheel filter, and a computer inside the system. Everything is placed on a PTZ. So a PTZ is a system moving like this, because the goal of this system is to scan a wide volume, and we make it move, take images, move again, and so on. So we build a very large image on mosaic, based on mosaic. So then we get the parts together. You can see the orange part are 3D printed parts, and there is an example of the software. A piece of a screenshot of the software. We add a temperature sensor and a rain sensor, because when it's raining, we put the system in a parking position to be sure there will be no too much water on the window. A small equation before lunch. So this is, of course, this was needed for the system. It's a radiometric calibration. Basically, if you look at what we did, so we use integration sphere to have a very uniform image going onto the sensor. And the equation looks like a flat field correction. And also, we convert by using calibration sphere, we convert the digital numbers from the image to radians. Here is some results. The image you see on the left is an uncalibrated image. So this is a raw image from the camera. And the image on the right is calibrated image based on what has been done during the calibration phase. The first system was installed in city of Toulouse, in southwest of France. So here there is one system working, and so it's scanning a large area in the city of Toulouse, and based on some other models that our customer knows about pollution, they were able to determine the exact position of the max pollution you have. Basically, it's around the big roads inside the city. So this system is able to detect NO2, PM1, PM2.5, SO2 and O3. It's experimental at the moment, and it's updated a map of the city every hour. So to conclude, sorry, I had to be fast because I start late. So we have a happy customer who puts confidence into us, and since the beginning, they say the news that we will succeed in this project. Thank you.
Thank you very much.
on time?
You stayed perfectly in time.
Do you have any question about this project?
Are there any questions concerning the realization of this very interesting application? Yeah, please.
Hello? Yes, thank you. Did you use extended range camera?
Extended, sorry?
A range camera, or was it a SWIR camera?
No, it's a UV visible camera.
Okay, okay.
And yeah, for future system, we will go to infrared. But for this first one, UV to visible was enough to.
How many filters did you have?
On the prototype, we put 6 filters, and now on the 2 systems we are finishing soon, there is 11 filters.
Okay, okay. Thank you.
Are there another question? Then I would like to follow up the question from the colleague. When you say UV, can you tell wavelength range a little bit more precise?
Yeah, we start at 280 nanometer.
Okay.
And on the second generation, we have 3 filters, 280, 300, and 310.
Ah, okay, okay, okay. Thank you, thank you. Okay, and concerning the question online, which was online asked, there are no further use concerning yesterday's videos appearing. So, yeah, there's nothing new online. Yeah. Okay, thank you very much for the presentation.
Welcome to our booth, All 10 C50.
Okay, thank you.